Okay, welcome to the penultimate colloquium of this semester, and it's a pleasure to have Provost Liss today giving us the update on the LHC. So for almost all of you, Tony needs no introduction, but let me do it anyway. So he earned his PhD in physics from Berkeley in 1984, and then he was a professor of physics at University of Illinois at Urbana-Champaign before coming to CCNY, where he was first dean of Division of Sciences, and now he's the provost. So he has several remarkable achievements in the field of physics. He led a groundbreaking research that resulted in the discovery of top quark, and he's also a member of Atlas collaboration that discovered the Higgs boson in 2012. So who better than Tony to give us an update on LHC today? So Tony, it's all yours.
Thank you, Sriram. So I actually had a different title up here, and then I realized I had given Sriram this title. So I'm going to talk about what we've learned from the LHC, but I decided rather than trying to give you a whole survey of all the results from the LHC, I picked a certain angle, and so that's one caveat, and the other is that I'm mostly going to focus on the Atlas experiment, which is the experiment that I'm on. You'll see some results from the other big experiments, CMS, and one from LHCb. And it's really, it's just convenience because I have easy access and I know where the Atlas results are. So it's a little bit of laziness, but the two big experiments at the LHC work hand in hand, and I mean the results are independent, but there's nothing that the Atlas experiment has done that's significantly different at CMS, which is both kind of boring but also lends us a good amount of confidence that the results are good when the independent other experiment gets comparable results. So I want to start with some LHC facts. I don't know that we have students in the audience. I was hoping we did. So some of this is pitched at undergraduates. So I think most of you probably know the LHC is this big 27 kilometer circumference accelerator that's on the border between France and Switzerland. And it's about 100 meters underground. So all you see here is a circle drawn on top of where the accelerator is. The old SPS accelerator at CERN, where the W and Z bosons were found, is now the injector for the LHC. This dotted line's the border between France and Switzerland. This is the Geneva airport. Geneva is off in this direction. The Jura Mountains are over here. And it's a fairly pretty spot. The Atlas experiment, the CERN lab is this, you can kind of see this triangle over here. That's the laboratory. The Atlas experiment is right about there. CMS is all the way on the other side of the ring in France. The accelerator's running, you'll see data that from the first run at 7 TeV and then at 8 TeV of center of mass, it's now running at, or was running at 13 TeV, and the luminosity is such that protons collide on protons at about 1 gigahertz. The accelerator has nearly 10,000 superconducting magnets in it, 1,232 dipoles, 394 quadrupoles, a whole bunch of sextupoles, and other magnets. It is filled, the magnets are kept at liquid helium temperature with 130 metric tons of liquid helium. So by far the largest user of liquid helium in the world. And we take about 30 petabytes of data a year. To give you a feeling for what that means, if the data were a movie on a DVD, it would be 250 years long. So the Atlas experiment looks like this. It actually doesn't look like the picture. it looks more like the drawing. The picture was taken very early on. It's actually the empty vessel for the Atlas experiment. So it's looking this way down the beamline. These are the Muon Toroids, which you see over here in this in the drawing. So this is before the most of the detector was assembled. You can see the scale. Here's a person violating safety protocol because here's his hard hat over here. But it gives you an idea of how enormous this thing is. It's 44 meters long, 25 meters in diameter. I'm not going to go through all the pieces of the detector. It has very fine tracking on the inside of a big solenoidal superconducting solenoid. Then outside of that is calorimeters to measure particle energies. And then outside of everything are muon detectors in another superconducting magnetic field from the toroids. So the physics goals of the LHC, I think many of you know, it's you can write it in many ways. Understanding the origin of the mass of quarks and charged leptons. All of these particles have zero mass in the standard model until symmetry breaking occurs, which gives them a mass. I'll talk a little bit about that. Neutrinos remain massless even after symmetry breaking in the standard model. That's because the standard model assumes that there are no right-handed neutrinos, and the mass terms require both left and right-handed fields. The biggest goal of the LHC is to search for new physics, and I'll try to motivate why we think there's physics beyond the standard model, abbreviated as PBSM. So the standard model, unfortunately, I've been saying this for my whole 40 years in this field, the standard model explains everything we've observed so far, except for a few things like why the Higgs boson is so light, what particles or what makes up dark matter, things like that are not explained by the standard model. So we kind of know that there's something else out there. And perhaps the LHC might help us understand why the universe has evolved from equal parts matter and antimatter into all matter. We assume that the Big Bang created equal parts matter and antimatter, and it requires, as Sakharov told us, a number of different criteria, one of which is CP violation, in order to explain how it evolved into nearly all matter. But the CP violation that we've observed so far is not nearly big enough to account for the transition that occurred in the universe. So we think there's another big factor, a big source of violation of CP symmetry out there. And so we hope that maybe the LHC would uncover what that is. So most of the results I'm going to show you today are from Run 2 at Atlas, which ended just about 2 years ago. Run 1 occurred at a center of mass energy, root S, of 7 and 8 T, first 7 and then 8 TeV. Little less than 5 inverse femtobarns was taken at 7 and then about 20 at 8 TeV. As you know, the Higgs boson was discovered towards the end of Run 1 in 2012. This is the run that most of the results I'm going to show you came from. There was almost 160 inverse femtobarns of data delivered, so 8 times what we had in Run 1 almost. At Atlas, we recorded 147, and about 139 of that was usable for physics. The other 8 inverse femtobarns had, a detector problem here or there, or some reason why we had to throw out the data. So that's a substantial amount of data, and CMS has almost identical numbers. In case you're not familiar with the basic language of high energy physics, I wanted to just introduce it here because I'm going to use these Feynman diagrams a couple of times. I'm not going to use it a lot, but I wanted you to understand that these are not just pretty pictures of what goes on. They are that. And this particular picture shows the annihilation of an electron and a positron into a virtual photon that then reconstitutes itself as a quark-antiquark pair. And this quark radiates a gluon, the force carrier for the strong interactions. So this is actually a process that has nothing to do with anything I'm going to show you today, because I'm going to show you all proton collisions and not electron-positron collisions. But nevertheless, the thing about this that's separate from just being a pretty picture is that it is a way of guiding you to writing down an integral to calculate the cross section or the rate of the process that you draw. And so each of these lines has a term in the integral. This photon has a propagator. All the vertices have coupling constants associated with them. So there are rules called Feynman rules, and you write down the rules and you do the integral, and you can calculate the cross section for the process. So when I'm not going to do any of that, and I'm not going to even talk about it again, but I want you to understand when I show these pictures that there's actually math and calculation behind them. And if there are any undergraduates in the audience, if you've taken quantum mechanics, there's a wonderful book by, I'm blanking on his name, David. Anyway, it's Introductory Particle Physics, David Griffiths, Introductory Elementary Particles, I believe, in which he walks you through all you need to know is undergraduate quantum mechanics, and you can calculate this diagram with a little help from David Griffiths. Okay, so let me start with the origin of mass. There's, in the Standard Model, the way mass occurs is that there's a what's called a Mexican hat potential. So that's an actual Mexican hat. The potential looks more like that. And the thing about this potential in the Standard Model is that it induces spontaneous symmetry breaking. So if you're sitting up at the top of this is the two-dimensional, three-dimensional, but the two dimensions are the field, the Higgs field in this case. Up at the top, the field is zero. It's a complex field, so it's got two components. But up at the top, the field is zero, but it's not a stable equilibrium point. And at some point, the field can roll down into this minimum over here, breaking the symmetry because it's got this nice circular symmetry. And once it rolls down, it picks a particular place. And this is a minimum of the potential that has a non-zero field. It's called the vacuum expectation value. We know what the value of that vacuum expectation value is from low energy weak interactions, neutrino scattering, and that. It turns out to be about 246 GeV. And from that, in the spontaneous symmetry breaking, you can calculate the mass of the carriers of the weak force, the W and the Z boson. And their mass involves this term, the vacuum expectation value, that 246 GeV, and it also involves something called the weak mixing angle, which is also well measured in low energy neutrino scattering. So this was all developed in the 1960s and 70s. And in 1983, I think it was, the W and the Z boson were discovered at CERN in that smaller accelerator that's now the injector for the LHC. And they were discovered at precisely the mass that was predicted by the Standard Model and this symmetry breaking mechanism. So the Standard Model Lagrangian, the thing that tells how everything works, is on this coffee cup. And the W and the Z masses come out of the symmetry breaking, and as does the fermion masses. And the fermion masses come from this third term. And I want to talk about that third term in a moment. But first, I want to just give you a feeling for how the masses come out of this non-zero Higgs field. So this is an analogy that I stole from a talk by Leonard Susskind, famous physics City College graduate and well-known physicist at Stanford. Um, so the idea is that you take a water molecule, and a water molecule has an electric dipole moment that points from the oxygen towards the hydrogen. And you put it in an external electric field, and that creates an energy split between these two orientations, with the field parallel or anti-parallel to the dipole moment. And in fact, that potential energy of the interaction between the dipole and the electric field leads to a mass difference between these two orientations of the water molecule, where the dipole moment pointing opposite to the field because of this negative sign leads to a slightly larger mass than the other orientation. Now it's unmeasurably small with any normal electric field, but the principle is that the water molecule is acquiring a mass from this field. So that analogy would work perfectly, except that if it were actually an electric field permeating all of space, giving particles masses, it would violate rotational invariance. So it can't, because the photon has spin 1. So it can't be a spin 1 field. It has to be a spin 0 field, which is what the Higgs boson is, because the spin 0 field doesn't pick out a favored direction in space, and so it doesn't violate rotational invariance. So that's the basic concept between the interaction of the field and the particles, giving the particles a mass. And it comes, why can't I advance? Okay, we'll do it that way. So it comes from this term in the Lagrangian, which is these are the fermion fields, the psi I and psi j. Phi here is the Higgs field, and this term y is just a number. And unfortunately, the standard model doesn't tell us what that number is. So we dial it in so that the mass comes out to be the measured mass of the fermions. So this is one of the big unsolved question, is what determines, we know where the masses come from, or we have a model where the masses comes from the interaction with the Higgs field, but we are unable to predict what the masses are. So we can make a plot of all of the masses, the mass scale, as a function of something that makes them on a nice line. And you know, this pattern that we see here is physics beyond the standard model, because we don't know what predicts those fermion masses. And this is something we'll be able to look at if this is the right model with the Higgs boson at the LHC. Right. Okay, so let me remind you about the discovery of the Higgs boson, and then I'm going to fast forward 6 years to where we are now. So this is the atlas plots from the discovery. On the left, you see the main discovery channel, which was, I'm sorry, it's not labeled here, but it's Higgs to gamma gamma, which I'm going to 2 photons, which I'll talk about. I'll show you where that comes from in a little bit. But it's basically a Higgs particle that decays into 2 photons. And so the invariant mass of those 2 photons reconstructs back to the Higgs mass. And so what you see here is a spectrum of diphoton invariant masses, mostly background, but then there's this little bump here. And that little bump, if you subtract the background, which you can fit just from the data, no fancy modeling is needed here. You just make the invariant mass plot and you fit the sidebands and extrapolate under the peak, and then you subtract and you get this little peak here, which doesn't look all that significant, but you can combine it with other modes. And here's another mode where the Higgs decays to a pair of Z bosons, and the points are the data points. The red and purple are backgrounds. And these different little peaks here are Monte Carlo simulated signals from different Higgs masses at 125, 150, and 190. So starting at 190, nothing there that matches the data, nothing there that matches the data, but at 125, you got these two data points up above the background that agree with the 125 GeV signal. So you combine these. There was also a channel that involved W bosons, and you get a very significant discovery signal. And the Higgs mass was initially measured to be about 126.5 GeV. The proton, by the way, is 900.938 GeV, just to give you a scale. So just about 130 times the mass of the proton. Now we go to run 2, and that's how the data has changed. These are the same two plots. Here's the gamma-gamma peak looking much more robust, and having removed the other Monte Carlo peaks, here's the 125 GeV peak in ZZ into 4 leptons. So each Z boson is decaying into a pair of leptons, an electron or a muon or a tau. I think it's actually just electrons and muons here. And then you make an invariant mass of the 4 leptons together, and it comes out. So, and the mass is shifted down a little bit to just about 125. This is a summary, again, from Atlas of all of the different channels in which we've seen the Higgs boson. So one of the important tests is to look at all of the different decay channels, and I'll show you reasons why in a moment, all the different production and decay channels that you can find for the Higgs, and see if they're all consistent, and if they're all consistent with the standard model. Here, this is just the 4 lepton and the 2 photon channels, but it's run 1 data, run 2 data here, the combination, etc. And then Atlas and CMS combined run 1 results are here. That's where the 125.09 comes from. It takes a long time for the 2 experiments to get together and combine their results, because we have to understand each other's systematic uncertainties and how to combine them and how they might be correlated. The statistical part of it's easy, but the systematic part takes a long time. So the run 2 combination hasn't been done so far. So the big question that this raises in terms of the standard model and physics beyond the standard model is, why is the Higgs boson so light? Why is it only 125 GeV when the standard model itself would tell you it should really run, the mass should run up to the weak scale, up to around a TeV or something like that. So this is sometimes referred to as the hierarchy problem in general, or an aspect of the hierarchy problem. And so I want to tell you what that is. So this is just a mass scale here, going all the way from, I guess it's a logarithmic scale, so from 1 all the way up to the Planck mass at 10 to the 19. The Planck mass, by the way, is the mass at which the Compton radius and the Schwarzschild radius are the same. And so it turns out to be a 10 to the 19 GeV. It's a place where we know there's new physics, because quantum gravity has to start being important, and we don't have a theory. So you know, we don't know where new physics is, but we know there has to be something that happens at 10 to the 19, because we can't even calculate anything there. So the idea is, you know, somewhere along here, there might be new physics. Now, if we think back to those Feynman diagrams, and you're doing a calculation, you're doing an integral over all of phase space. And if there's no new physics anywhere between, you know, low energies and 10 to the 19, that integration is going to go all the way up to 10 to the 19 GeV, at which point you have to stop, because there's new physics and you don't know what it is. So if you imagine that there's a scale of new physics somewhere else, somewhere below 10 to the 19, just indicated by this line, then you would do your integration up to about that point, and then you would stop and evaluate what your uncertainties were for stopping the integration there. So we don't know where that new physics is, but we think, and I'm going to tell you why in a moment, that it's somewhere below 10 to the 19 GeV. All of the stuff that we measure in the Standard Model is down here at hundreds of GeV. So let's go back to the Higgs mass. If I were to calculate the Higgs mass, which by the way we can't do in the Standard Model, but just as a thought experiment, I would put in a term that I'm going to call the bare mass, which we can't calculate. And then there are corrections to the mass. And the corrections to the mass we can calculate. They come from things where the Higgs boson, this is a Higgs boson, these are little Feynman diagrams, and the Higgs boson splits for a moment into a top anti-top pair, we called a top quark loop, that can come back together into the Higgs boson. So that's one piece. There's another piece where it radiates a vector boson. There's another piece where it radiates a Higgs because the Higgs can couple to itself. And all of these terms go into this little thing I'm calling delta m squared. Turns out that these two loops, the vector boson loop and the Higgs boson loop, only depend logarithmically on where that cutoff is, where you think there's new physics that you have to account for. But the top quark loop turns out to give you a term that looks like this and depends quadratically on that cutoff term. This thing y squared in the numerator is that coupling in the Lagrangian. It's the Yukawa coupling, which was Yij in the other equation. This is the y for the top quark. And it turns out to be very close to 1.0, which is an interesting thing. So the problem is that this gives you a term that goes quadratically like the cutoff. And so if you imagine that there's no physics up to some very high mass scale, this lambda squared becomes very large, causing this delta m to become very large. And in order to come up with a small observed Higgs mass of 125 GeV, you have to dial in a very precise value for this bare mass that you can't calculate. You have to, if the two terms, you're adding two terms together that are very large and getting something that's relatively small. And that's not appealing. It's referred to as fine tuning. It's referred to as the hierarchy problem. But it's definitely not appealing. And so you would like to find a way around that in order to have confidence that your theory makes sense. And so the most popular way around that is to introduce another symmetry called supersymmetry. And in supersymmetry, there's a fermion. For every standard model fermion, there's a supersymmetric boson. The simplest theory of supersymmetry is the minimal supersymmetric model. And vice versa. For every standard model boson, there's a supersymmetric fermion. So for the gluon, there's a gluino. For the top quark, there's a stop quark, or sometimes referred to as a top squark. And in supersymmetry is also a broken symmetry because the particles and their superpartners have different masses. We know because we haven't observed any of the superpartners, so they have to be heavy. The minimal supersymmetric standard model includes a second Higgs doublet, so it has a richer Higgs sector that I'll talk about, and it has a second vacuum expectation value. So one of the Higgses gives masses to the up fermions, the other gives masses to the down fermions. And interestingly, the lightest supersymmetric particle can be stable, and if it is stable, it can be a dark matter candidate. So there are lots of reasons to think this is a great theory. And one of those is that it solves this hierarchy problem. The top quark loop that gave that quadratic divergence is almost canceled by the loop that comes from the stop quark or top squark. I did not invent these names. And so if you add these two terms together, you end up with something that's much better behaved. It's again logarithmic like the other two terms I showed you in this cutoff mass lambda. So as long as the top and the stop masses are not too different from one another, which would cause this term to get really big, then this solves this fine-tuning problem adequately. So one of the things we do at the LHC is to look for stop quarks. And the way we look for them is by looking for them to be pair produced. Anything with this little tilde on top is meant to be a supersymmetric particle. So these are stop quarks and a stop antiquark or an anti, whatever. And then each of them decays into a standard model top quark and this thing chi10, which is a weakly interacting lightest supersymmetric particle, or an LSP. Sometimes there's a chain of decays, a cascade that goes ending up in this final state. But the basic idea is that you're going to produce a pair of top quarks, because each of these is decaying along this channel. So you'll have a top and an anti-top, and you'll have two of these chi10s. So what you look for are events that look like top quark production, but have anomalously large momentum imbalance, which we refer to colloquially as missing transverse energy or missing ET. But it's momentum imbalance because these particles, these chi10s, are escaping the detector without leaving a signal. They interact only weakly, and so they go like neutrinos all the way through the detector, carrying off momentum that we don't measure. So when we look at the whole event and measure everything in it, we see that momentum in the transverse plane is no longer balanced. The proton and proton are colliding longitudinally along the beam axis, the z-axis, and so the initial momentum in the transverse plane is essentially zero, and so should the final momentum be. Whoops, wrong way. And so here's the result of the searches for stop quarks from the ATLAS experiment. And this is a combination of run 1 data and run 2 data. And what you see colored in here are all the places where we haven't found the top quark. These are regions that are eliminated at the 95% confidence level. And the two dimensions are the mass of this chi10, because we don't know that either, and the mass of the stop quark. And this line, above this line, which would be at 45 degrees if the two axes were the same. I guess it is 45 degrees, it just doesn't go through the origin. That's the place at which the mass difference between the stop and the chi is zero. So when you have this decay scenario, if the mass difference between the stop and the chi is zero, then the top quark there's no Q value left over for the top quark to be observed to have any, you can't go beyond that point because of energy conservation. So this region is excluded by energy conservation. So you can see we've not eliminated the whole phase space, but we've eliminated much of it. And the argument that the stop quark is light enough to solve the hierarchy problem is getting strained, I would say. So another question we can ask about the Higgs is whether it actually looks like the Standard Model Higgs. The Standard Model Higgs has spin 0 and positive parity. So we can look at the decay channels and see whether it looks like it has spin 0 and positive parity. We can also look to see whether the couplings, sorry, I'm talking about this backwards. We can see whether this term in the Lagrangian that determines the masses is really a term that tells you how strongly the Higgs couples to the fermions, and it couples with a strength that's proportional to the fermion mass. So it couples to the top quark, the heaviest known fermion, most strongly, and to the electron, the lightest charged fermion, leaving out neutrinos. It couples to the electron most weakly. And so we can look at its decay patterns and see whether it agrees with that expectation. We know, as I said, we know what the masses are, so we know what the value of Yij is. We just can't predict it, but we can measure it. And so here's the result from run 2 of the coupling of the Higgs boson to a variety of different, not just fermions, but also the W and Z boson. So here's the muon way down here. The coupling is very weak to the muon, and so it's hard to measure, and it hasn't really been observed. We require a stronger statistical significance to call it an observation, but there's a measurement with a large error bar that's not inconsistent with the expectation from the standard model. Here's the tau lepton, the B quark over here, the W and the Z boson, and the top quark up here, and they all lie very nicely on the expectation for a standard model Higgs boson. And this is important because remember I told you that in the minimal supersymmetric model, the two different Higgs particles, the Higgs doublets, provide mass to the bottom quarks and the up quarks separately. And here we have the single Higgs boson that we observed so far, apparently giving mass or coupling to both the bottom quark and the top quark. This point up here for the top quark, I want to stress, because this is important, how strongly I want to draw that conclusion, that this point is inferred. It's not directly measured yet, although I will, there's a caveat to that. It's the point that's drawn on this plot is not from a direct measurement. Let me say it that way. What it comes from is looking at the production and decay of the Higgs boson. The Higgs couples to mass, which means it does not couple to things that are massless. And yet we observed it through Higgs to gamma gamma. And the way that occurs is through a loop of top quarks. You can also put W bosons in this loop at the top because it's heavier is most important. And the top then radiates the photons. So the Higgs does not couple directly to the photons, nor does it couple directly to the gluons, which are most of the collisions between protons and protons are gluon-gluon collisions inside the proton. There's another top quark loop on this end. There are other production mechanisms that I'll show you in a moment, but this is the primary one. And so when we look at how Higgs is produced and decays, and we compare it to the standard model, we're assuming diagrams like this. And when it agrees with the standard model, we go, great, that's the right diagram. But it's possible that there's other stuff going on in these loops, that there's physics beyond the standard model. And, conspiracy theories are very popular these days. There can be a conspiracy where things add up and cancel out in just the right way that it looks like the standard model expectation, but it's not. So until we directly measure the coupling of the Higgs to the top quark with this kind of precision, we can't really make the statement that I was starting to make there, that we've got coupling to a bottom and a top quark from a single Higgs boson, which would sort of rule out the two Higgs doublet model. So here are all the different production mechanisms for the Higgs. I said there was more than just glue. So this is the one I showed you on the previous page. But there's also what's known as vector boson fusion, where a W or a Z is radiated off of the incoming quarks, and they fuse into a Higgs. There's what's called Higgs-Strahlung, like Bremsstrahlung, but radiated off of a W or a Z. And then there's this diagram, um, which is the direct coupling to a top quark. This is a TTH production, we call this. It's the production of a pair of top quarks along with a Higgs boson. And so this is the holy grail for actually measuring directly the coupling of the Higgs to the top quark, because you observe the Higgs, for example, in its decay to ZZ or gamma gamma. You observe the top quarks because you can reconstruct their mass. And so you know to a high degree of certainty that this is what you're looking at, and you can measure the rate at which it happens and measure that coupling. And so that's something that's very new. And here's the data. This is that same diagram. The angle of these two internal top quark lines in that other diagram had no meaning. So this is the same diagram. And here's the data from ATLAS, and CMS has a similar result. Let me walk you through this. Here is the CMS result. So this is the diphoton invariant mass, like in the Higgs discovery, except in events where a top quark has been, or a pair of top quarks has been identified. And you see that there are events that are clustered here consistent with the Higgs production. And so here you can look at all of the different ways we could observe this. This is ATLAS. CMS is looking at the same thing, also all the different ways that they've observed the same process, only they categorize them by the number of leptons and the number of taus, and SS means same sign and OS means opposite sign for the charge of the leptons.
So there is a question from Parmeshwaran.
Yeah.
Parmeshwaran, go ahead.
Well, I was going to ask Tony, but first of all, hi, I haven't seen you for a long time. The question is, you talked about the measurement of the B coupling to the Higgs directly, but the top could not be measured directly, but they are part of the same doublet. So don't you get some constraint from that?
Well, the top, so I don't think you get a constraint because the Higgs couples independently to the bottom and the top. The only way you can measure the coupling is actually observing this process or the Higgs to BB process.
Okay.
I mean, it's just a direct experimental measurement.
Okay. Thank you.
Okay. So these are showing the same kind of result in split up different ways. They're both comparing the ratio of the measured cross section to the expectation from the standard model. So that's this line at 1 with some uncertainty band, and CMS is calling it mu, but it's the same thing. And they're splitting their data into different channels, and ATLAS is splitting its data. But what you can see, it's not a very precise measurement. The combination from ATLAS is here, a little bit greater than 1, but with an error bar that's big enough to be consistent, very consistent with 1. CMS, the combination is a mu, the same number, but called mu, that's a little bit less than 1 with a big error bar that's clearly consistent with 1. And, it hasn't been done yet, and it'll take some time, but, you can look at it yourself. You combine 0.92 with, 1.4, whatever this is, you're going to get something 1.32. You're going to get something that's even more consistent with 1. So, it's not very precise. It's not nearly as precise as what I showed you on that previous slide. But, it's looking a lot like the standard model coupling of the Higgs to the top quark. So what about looking for other Higgs bosons? These two Higgs doublets give you a much richer Higgs sector in supersymmetric models. For example, in the MSSM, there are 2 CP even neutral Higgs, little lowercase h and uppercase h. There's one that's CP odd, that's called A, and then there are 2 charged Higgs bosons. And so you can look for those. We don't, the only thing we know is that, before I tell you anything else, the only thing we know is that the one we've found is not the charged Higgs boson, but it could be any of the others. And so first of all, looking at the spin and parity of the Higgs to see whether it's even or odd in parity. This is a very subtle and tricky thing to do, which you can see clearly from this plot on the left. This is Higgs going into 4 leptons, a pair of Z's to 4 leptons. And what you're doing is measuring the angular distribution. So this cos theta is the angular distribution variable. And the dashed line and the solid line are respectively, both are spin 0, and one is odd parity and the other is even parity. So the solid line is the standard model. And you can see it's awfully hard to distinguish the data points from either of these models at this point. And this is only run 1 so far. It'll be much better in run 2. Over here is Higgs to gamma gamma plotted in a very user-unfriendly way. But you're looking again at an angular distribution in the first 10 bins of this plot. I have a lot of problems with how my collaborators decide to display data because nothing is intuitive. But this is really just another cos theta distribution, except for the last bin, which is a PT bin. So I'm sorry, but that's what they did. And so what you see here is the difference between, this is now the standard model 0 plus. You could also imagine that it might have spin 2, might be some kind of graviton or gravitino like object. And so you can compare to spin 2 models, which are these different colored distributions. And here you can actually have some discriminating power, although not a great deal. And the plot on the bottom is a statistical parameter with a combination of these data and data that come from W pair, Higgs to W pairs. And here you see this black line is the measured point in this statistical discriminant, and the distributions are what you expect, what you generate by doing Monte Carlo experiments over and over again with a standard model 0 plus or some non-standard model negative parity Higgs boson. And so you can see the negative parity Higgs boson is pretty well ruled out. And from these you can rule out spin 2. It's not a case closed, but when the results from the 13 TeV run with 8 times as much data come out, these things will become much more precise. So what about looking for the A, the CP odd Higgs that's expected in supersymmetric models? And so that's been done by looking again at different angular distributions in Higgs decays. This plot actually also on the right-hand side from Atlas also includes some charged Higgs searches and nothing is found. And you see these regions that are colored in as a function of MA versus tan beta. This is the beta is the ratio of these two vacuum expectation values, which is unknown. So you have to scan over tan beta and look as a function of MA. And so you can see there's some region here in very large A mass and low tan beta that's not excluded, but the map is getting filled in by both CMS and Atlas. So nothing in terms of supersymmetric Higgses yet. And charged Higgs searches. The charged Higgs behaves a lot like a W boson. So it can decay into a top and a bottom pair, just the way the W, if it were heavy enough, would decay. The original searches for top quarks were in W boson decays, looking for exactly this process from a W, but it turns out the top quark is too heavy. But if the charged Higgs is heavier than a top plus a B mass, then it can decay that way, and that's a popular way of looking for it. And I'll just cut to the chase because I'm running out of time, that there's nothing found, and you can place a limit on charged Higgs mass. The exclusion limit, you place an exclusion on the cross section for the production and decay of a process like this. That exclusion line is this jaggedy black line. The dashed line is the expectation for the exclusion from Monte Carlo, and the green and the yellow, this is a so-called Brazil plot because of the colors of the Brazilian flag. The green and the yellow are the 1 and the 2 sigma uncertainty bands on the expected limit. And then this red curve is the calculated cross-section times branching fraction for a Higgs as a function of its charged Higgs as a function of its mass for a tan beta of 0.5. The blue over here is tan beta of 1, and the magenta is tan beta of 60. So you can see as tan beta goes up, you lose your sensitivity pretty rapidly, but it also just kind of clusters around here. So we've ruled out a charged Higgs mass of around a TeV for tan beta of 0.5. And you can read off your favorite tan betas from this curve. So what about just comparing everything that we do measure in Higgs to what we expect from the standard model? Because if there's some non-standard model stuff going on, maybe it's subtle, maybe we don't know what to look for. So let's just look at everything and see how it compares to the standard model. And so that's what this is. These are different production mechanisms. Remember that graph I showed you before with all the production mechanisms. So this is gluon-gluon fusion. That's the major production mechanism. This is vector boson fusion. That's where the W and the Z were coming together in the middle of the Feynman diagram. This is Higgs-Strahlung, where the Higgs is radiated off of a vector boson, and this is the TTH channel. And then in each of these subcategories, the different points are different Higgs decay channels. And so, you look, and then this is the ratio of the cross-section to the standard model expectation. And you look, and there's nothing that's really significantly off. And if what people usually do is you take all these numbers and you make a histogram of them, and they should look, if you know what you're doing, they should look like a nice Gaussian with a mean of, in this case, 1 and a width of 1. That if the width comes out right, that tells you understand your uncertainties right. You're not overestimating or underestimating them. And if the mean comes out in the right place, that tells you that you're not biased in some way. So no sign of anything particularly funny going on there, but there's still some pretty crude measurements, and so there's more to be done. We can also search, of course, directly for new particles without worrying about the Higgs boson at all. You just look for the production of supersymmetric particles in the way I described the search for the stop quark before. And the bottom line is we haven't found anything at all. And so we make plots like this, which look very lovely. And there are searches. Each of the band is an exclusion in the mass scale. So a TeV is this shaded line here. Before the LHC turned on, there were lots and lots of papers telling us that supersymmetry was going to be found at the TeV scale. So that's why we look at a TeV. And part of the argument, that is from the stop quark mass argument. Up here I'm sure you can't read this, and I can barely read it myself, but up here are inclusive searches for squarks and gluinos. These aren't even all, these are all SUSY searches. I'll show you non-SUSY searches. These are third generation squark searches. So these are the stop searches here. These are what we call Wino or Xeno or Wino searches, electroweak, the supersymmetric particles of the W and the Z bosons. Long-lived supersymmetric particles have a special category because if they live long enough to get outside of the inner tracking detector, you have to look for them in special ways. And then these are, I forgot to mention R parity, which is a very important thing. When if you remember in the way the stop quark decayed, it decayed into a top quark and that lightest supersymmetric particle. The reason we think there's a supersymmetric particle at the end of the decay chain is because of something that's invented called R parity. And it was invented to prevent the proton from decaying too rapidly in supersymmetric theories. And so it requires that the number of supersymmetric particles on either side of the equation is the same. So we produce supersymmetric particles in pairs, and when they decay eventually into a lightest supersymmetric particle. And that allows supersymmetric theories to have dark matter candidates, which is that lightest supersymmetric particle. These things down here called RPV are R parity violating searches. So searches where you don't assume this made up R parity is conserved. You lose the probably the dark matter candidate that ends up at the end of it. And the searches become much harder because it's much harder to know what to look for, but you can still do them. And so a lot of the focus is turning to R parity violating searches because we haven't found anything with our R parity conserving assumptions. This is from CMS, and this is all the kinds of searches, same plot, but all the things that are not supersymmetric searches. So supersymmetry is just a theory, right? It might be something else. There's extra dimensions, there's quark compositeness, there's scalar leptoquarks, there's, new resonances, all kinds of stuff you can imagine you can search for. The only problem is you can't find it. Again, here's this right here is a TeV mass scale. So, a lot of space has been ruled out, but the imagination of theorists for what could be out there is infinite. So, another way to look at this is just, like we did with the Higgs, just compare everything we can measure with the standard model expectation. If there's anything funny going on, then, we might see it in some measurement in the standard model that doesn't agree with our expectation. Maybe because in one of those little loops that we have in the Feynman diagrams, that occur in lots of different processes, maybe one of them includes some supersymmetric component that changes what we would measure. So we do that. And this is a plot of not everything you can think of, but a lot of things you can think of. Up here is the inclusive cross-section for proton-proton scattering, the inelastic cross-section for proton-proton scattering, and then down at the bottom, it's arranged in order of the size of the cross-section. Down at the bottom is the production of a pair of Z bosons with multiple jets. And this plot on the right are all of the values divided by the standard model expectation, what we measure divided by the theory, and it all looks awfully good until you get down to the bottom where the error bars get big. So there's not really a sign of anything new going on there either, but it is an absolutely amazing tour de force. It boggles my mind how well the standard model works. You know, it's really just a remarkable, remarkable theory. You know, what is this? 2020. So we're 40 years past the, 50 years past the, development of the standard model. And it's just, remarkable that it works as well. That's all I've got to say. So we have 10 years of LHC data. We've discovered a grand total of one new particle. It is, I don't want to poo-poo the one new particle. I think it's an absolute miracle that the discovery of the Higgs was a kind of miracle in itself. But the fact that the particle that was discovered looks so much like the standard model Higgs boson, which is just the minimal thing that was written into the theory by three guys, there's not really any reason to believe that that is the right thing. And so before we discovered the Higgs boson, my money was on the Higgs sector leading us into new physics. And it's looking more and more like that may just not be the case. I mean, it may still happen, but it may not. There doesn't appear to be anything surprising about this particle, which is the most surprising thing about it. And everything else looks just like we expect from the standard model. So what do we make of it? Where's the physics beyond the standard model? One possibility is maybe SUSY particles are there, but they're really heavy and we haven't been able to produce them. Maybe there's no supersymmetry, but there's some other new physics that explains why the Higgs mass is so light and solves the hierarchy problem. Maybe that whole idea of naturalness, that we can't do fine tuning, maybe it's just wrong. What's wrong with fine tuning? There are there are people who believe that the universe is part of a multiverse, and maybe the dice are rolled for what the constants are in every multiverse, and the fine tuning problem is solved because we're one of 10 to the 19 multiverses, so you can fine tune at that level. That sounds a little crazy to me, and I once at a conference asked John Ellis, who's a theorist at CERN, who's one of the big proponents of supersymmetry, and someone who'd just given a talk, Alan Guth actually, who invented the multiverse, and had just given a talk about the multiverse in which he said this was the solution. And I asked John Ellis what he thought about that. And John Ellis is a very nice, mild-mannered man, and he was furious. He thought it was the craziest, silliest, ridiculous idea he'd ever heard of. We do know that there's dark matter, so we need to solve that problem, and it doesn't look like novel theories of gravity are doing it for us. So it does appear to be a particle that we haven't discovered. Getting back to the possibility that supersymmetry is, I'm almost done. Getting back to the possibility that supersymmetry, maybe the particles are just really heavy. We can have access to very heavy particles through these virtual loops that I've referred to a couple of times. And one of the popular ways to look for that is you look for something that's very rare in the standard model. And then, if it's very rare and you can see it at some enhanced level, that means that something's going on. So B sub S to mu mu is one of these processes, and B sub D to mu mu is its partner. And it occurs through a loop, which in the standard model includes the W bosons, which can turn which turn up quarks into down quarks and vice versa. And so you can have a little loop of W bosons that then couples to a Z, which decays to a pair of muons. And these are, because these are virtual particles, they don't have to be on the mass shell. They don't have to be at their nominal masses. They can be at some other mass that you can access at LHC energies. So the virtual loops might include new physics. And so this measurement has recently been done. And here it is in 2014. So this is a plot of the measured rate of the B sub D to mu mu versus B sub S to mu mu. So the loops should be the same physics going on, but the rates are different because it's different quarks involved. And so this is the initial measurement. And the square is the measurement. And here's the standard model over here, which looks like it's about to be ruled out at the 95% confidence level limit. So that, caused a fair amount of excitement. This, by the way, is a result that's a combination of CMS and LHCb. LHCb is the one of the special purpose experiments that's designed just to do B physics. So it's really designed for this kind of measurement. Fast forward 4 years later, and here's where we are, between 0.1 and 0.2. So another bit of excitement seems to be disappearing. It seems to look like it's consistent with the standard model. So what's next? Well, run 3 is scheduled to begin in the middle of next year and run for quite some time through 2024. About twice as much data as we have now. But the energy is going up to 14 TeV from 13. That sounds like a small amount, but when you're trying to produce very heavy particles, small increases in the center of mass energy can lead to large increases in the production rates. So that shift will be important in extending the mass reach. After run 3, the LHC will be upgraded, not in energy, but in luminosity. And that's a shame because the reach in mass is much slower as the luminosity increases because you're dealing with the tails of structure functions in the proton than it is if you dial up the energy. But dialing up the energy requires making new magnets and a whole new accelerator. So they're going with high luminosity. The high luminosity will give an order of magnitude more data than run 3. And so what that's getting for you in terms of the precision on Higgs measurements is shown in this plot. So this is where we are now. These are just the cross sections for gluon-gluon fusion, vector boson fusion, the different production mechanisms for Higgs. These are the uncertainties that we're at now, and this is where we'll be. So for example, in TTH, we have a 20% uncertainty now, and it will be 5% with the high luminosity LHC running. So improvements there, but they're not dramatic improvements. They're significant, but they're not dramatic like they would be if the energy were going up to 50 TeV or something. So maybe physics beyond the standard model is just around the corner. I've been hearing that for 40 years. So maybe it is. Maybe it's somewhere. There is dark matter after all. So thank you.
Thanks, Tony, for a wonderful talk. And so are there any questions, Tony?
I have one more question, if I can ask now.
Yeah, sure, go ahead.
You mentioned CP violation at an early stage in your talk as one of the things that might tell us a little bit about the matter asymmetry of the universe and so on. And also, I mean, when you have multiple Higgs, of course, that's one way you might get other channels of CP violation.
Right.
But are there any other things that LHC would look for in terms of CP violation?
Well, I mean, LHCb is looking at CP violation in the B system, but I think we already know that that's not dramatically larger than we expect.
Right.
But that's really one of the focuses of that. You know, we look for it. I mean, people do searches for CP violation and top quark decay. I mean, every new thing you can do is being done. Those things, you know, we hope that they're large enough to observe, but it's at an experiment like Atlas, those are tough things to do. I think the best hope for understanding where the CP violation comes from is something that the LHC does nothing with, and that's a neutrino physics, where there's now some hints that there actually is CP in the neutrino sector. So I think that for that particular angle, I think that's probably where it's going. But yes, I mean, the hope was that you know we would see multiple Higgses and there might be some extra CP violation observed there, but not so far.
It seems like standard model is way too successful. I guess that's a problem.
It's really quite amazing.
Yeah, it's incredible.
For a theory that everybody knows is wrong, it sure works well.
I have a tangential question. When you showed us the various data that were collected by CMS and Atlas, etc., and eventually they were reconciled, say for the mass of the Higgs, there were some pieces of data that their mean and their deviation was way off. How do we justify that? Do we say that they were just a statistical fluke, something went wrong with the experiment or the conditions? Are we concerned at all about the existence of those data, or we just dismiss them and they say the average is that?
I'm not sure. Are you referring to something in particular?
I mean, well, I saw some of the early data that you showed that you were collecting CMS data in Atlas, and eventually they converged to a mass to the Higgs with some statistical accuracy. But I remember there were at least one bar that was way off, including its kind of 2 sigma standard deviations. And of course, you can say that the rest of the data make up for what you want to calculate. But how do you interpret the existence of that part of data? Was it just an unhappy occasion, a very rare event?
Well, I mean, I think, you know, you're always excited a little bit by those, but when the uncertainties are large, you have to wait and acquire more data and see whether the mean begins to shift to where you expected it to be, or whether it stays in the same place and the error bars shrink. You know, I mean, it's always possible that you've underestimated your uncertainties. It's, you know, the systematic uncertainty estimation is really an art form. I mean, when we do when we do an analysis, and I mean, you know, I've flashed through these plots, but the hardest part of any analysis is understanding what the systematic uncertainties are, and then convincing the rest of the collaboration that you understand what they are, because it's really an art form. The statistics is just math, but the systematics, you've got to figure out ways to estimate it. You've got to figure out ways to validate your estimation, and it's so it's the easiest thing to get wrong. And so sometimes things are way off because you had a big systematic uncertainty that you underestimated. But most of the time, it's just, you know, when you're measuring 100 things, 5 of them are going to be, you know, 2 sigma away from where you expect them to be. And We
Okay.
measure a lot of stuff. That's why when I referred to making a histogram of all of those cross-section divided by standard model expectation values, and you expect to see if you subtract 1 from that, you expect to see a mean of 0 and a width of 1, which is this tells you that you've got you've done your analysis correctly. If you see a shift away from 1 or a broad distribution, then something's wrong.
Right.
Tony, I have a naive question. So why are we so sure that there is dark matter?
A lot of different ways to look at it. There's there's the rotation curves of galaxies and rotation curves of galactic clusters that just Newtonian gravity tells you that there has to be more mass inside than we measure from the light. But
so have they ruled out Mond type of theories for
sorry,
that? Have they ruled out modified Newtonian dynamics kind of theories?
Nothing is ever ruled out, but it's inconsistent with a lot of data. And there's this very famous picture of these two colliding superclusters, which is measured in the X-ray, and you can actually see the drag of the dark matter behind the normal matter, or vice versa. I forget which way it is, but you can almost visibly see the dark matter in that collision of the two superclusters, because it doesn't. I used to have a plot of that handy, but I'm not describing it very well. But that doesn't rely on anything but the gravitational attraction.
Yeah, I think I've seen that animation actually. Yeah, because I kind of once was in a colloquium at Simon Center by Martinus Weltman, and he was literally berating dark matter. And
he was what?
He was berating dark matter, and
yeah, it's popular, and it might be wrong, but nobody's come up with an argument that I find very convincing for why it's wrong. It's
and at what point people will start accepting that supersymmetry may not exist? So is there, or it's kind of unfalsifiable at this point? They'll go heavier and heavier in masses.
I don't think we'll ever rule it out completely. It'll just become inaccessible. But the other dark matter, I mean, the CMB requires dark matter also. There's all sorts of places where you need dark matter in the model in order to make it fit the data.
Okay, so are there any more questions for Tony? So if there are no more questions, let's thank Tony once more for a wonderful talk.
All right, thank you, everybody. It was
Thank you.
fun to get this instead of my usual day job.
Excellent.
Very nice talk.
We can make it a every semester event.
Yeah.
I'd be sorry.
We should schedule it at the review committee meeting time, so we can get out of it.
Right. Okay, take care.
Okay.
Bye-bye.
Bye.